All right, so today's lecture is finally about applications of Yang-Mills theories, particularly the first and most important application to quantum chromodynamics, or QCD. So we'll define what QCD is, and then talk about deep inelastic scattering, which is the most important experimental application. So QCD, I mean, what's important is to understand, so QCD at high energy, as we saw, it's any gauge theory at any gauge theory with few fermions at high energies is asymptotically free. So that means that if you increase the coupling, if you increase the energy of the scattering, then the coupling becomes weaker, so you can test easily with perturbation theory. But at low energies, it's different. At low energies, we don't have much other than experiments. So we would have to understand non-perturbative properties. So we will say a few words about that later on, but in this lecture we'll concentrate on a combination of high energy experiments with some low energy data. So first of all, what is QCD? QCD is a theory of quarks and the gluons with the gauge group SU3. And there are 6 flavors of quarks. Flavors because, well, historically SU3 was thought to be called a group of colors, as in the 3 colors that we have on your TV screen, with which we can build everything. Red, green, and blue. So then from this came flavors. I mean, somebody thought of the opposite. What is, if you have colors, the other things would be flavors. And these are divided into 3 families or generations. So we have, so the quark model was introduced by Moray-Gell-Mann, and Zweig. And the quarks are up, down, charm, strange, top, bottom. And the element on the top line, that is up, charm, and top, have electric charge +2/3. And ones in the bottom, that is down, strange, and bottom, have -1/3. And you can ask, if we have 3, why not 4, 5, and so on? Well, we know we have 3 generations, both from particle accelerator experiments. For instance, from the decay of the Z0 particle. Well, I guess we'll talk about it, or maybe not. No, yeah, I think we'll talk about it when we talk about electroweak symmetry breaking. So from the cross section for the decay of this particle, we can infer that there are at most 3 generations, and also from some constraints from cosmology, we know that there are 3 generations. So these are all the quarks there are. Now, when I said generation, well, we have these doublets, but correspondingly we also have 3 families of leptons. So the leptons are electron and electron neutrino, muon neutrino, and tau neutrino. And together these, so let's say the quarks up down and with leptons electron new electron form one generations, and so on. The low energy states are gauge invariants, since the theory is confining at low energies. What that means is that because the coupling becomes very strong, because at low energy the gluon force is very strong, that means that we obtain a linear potential between quarks. So a potential that is approximately equal to a tension times the distance between the quark and antiquark. That presents from breaking them apart. So only uncharged, that is gauge invariant objects, are don't have this potential, because there's no. So this potential is on something with charge. So QCD states are generally called hadrons and are divided into mesons and baryons. Mesons are pairs of quark-antiquark, of which the lightest objects of QCD are the pions pi plus minus and pi 0. Then we have the baryons, which are objects with 3 quarks, QQQ, and that includes the proton. The most common are the proton, which are up, up, down, and the neutron, which is down, down, up. You can check that the charge is what you expect. It's so see if you have up, up, down, charge would be 4/3 minus 1/3, that's +1. And if you have down, down, up, you have minus 2/3 plus 2/3, 0. So that's a neutron. In terms of color indices, when I say Q bar Q, I mean really Q bar with I up and Q with I down. Or you can define it the other way around. But the point is that there's a delta ij with an index down and another index up. And ij are, of course, fundamental indices going from 1 to n of the gauge group. So it's Q bar Q contracted with a group invariant delta ij. That it's an invariant that relates the fundamental representation n with an anti-fundamental representation n bar. On the other hand, the baryons are objects that are particular to the group SU3. So this Q bar Q would be true for any SUN. But for SU3, we have this QQQ, which specifically means QI, QJ, QK, contracted with group invariant epsilon ijk. Of course, this could be for SUN. I could write epsilon I1 up to IN, QI1 up to QIN. That would be an invariant. Now, at low energy, there's also the approximate global symmetries of the Lagrangian that's called isospin. that rotates up and down quarks. So there's an SU2 matrix that acts on U and D and rotates them. All right, so this was QCD. Now let's see what we do with them. So we know that we have so the states that we observe at low energies are, well, mesons are harder to produce. They don't exist in the vacuum state. They decay. But we have baryons. We have protons and neutrons, and of course we have electrons. The neutrinos, maybe we have, maybe we don't, but since they interact very little with matter, it's hard to detect. So anyway, the point is that what we really have available to us to do experiments are electrons, protons, and neutrons, and their antiparticles, of course. So deep inelastic scattering, that's one important experiment, one of the most important ones. So it's something that involves the scattering of an electron of a hadron, but usually the hadron is the proton. The reason is, of course, that the proton has charge, and so does the electron. So that means there would be an electromagnetic force between them. So you will be the electron will interact with the proton, and in particular, it will interact with some part of the proton that we'll describe before, but that part is obviously has to be a quark, right? Because a quark is charged as well, and so we can have an interaction via a photon, and then the quark itself, well, cannot exist by itself, so in principle has to create at least another particle, or maybe join back the other particle. Okay, so why would you do this experiment? Why not say proton on proton? Well, we could do that as well. It's just that the first thing, and people do proton-proton or proton-antiproton experiments, but those are for beyond the standard model. But why for QCD this is not a good idea? Well, because what do we think about QCD? Well, the proton is something that has some structure, has a size, and there's quarks bouncing around and that are bound together by this gluon force, this linear potential. So we want to probe that, and if we bang together two of these guys, we will not learn very much about the structure. What we should do is to probe it with something point-like the electron. So that's why this is a good example of a model, of an experiment. All right. So the electron probes this structure by breaking it, and as I said, through this electromagnetic force, the photon, you interact with a quark inside it, and therefore the reaction can be called, so you start with an electron and a proton, and you end up, excuse me, with the same electron. The electron remains, of course, and then with state X, that can be one or more hadrons. The point is, since you pull out a quark, then the quark cannot exist by itself, as we said. So it will, if it will not interact with these remaining quarks, at least it will interact with the vacuum and create quark-antiquark pairs. Anyway, the point is that the result in here might not be proton itself, but some other combination of hadrons. Okay. Now, how do we describe this proton? I mean, I said that there's up, down, a combination of quarks. But when I said that, I really meant that that is what happens at high energies. In high energy experiments, we see that the structure is composed of up, down quark. So that's in perturbative gauge theory. But what about the vacuum state, the state that it's at low energy, that a proton that we have in nature? How do you describe that? Well, for this non-perturbative proton, Bjorken and Feynman proposed the so-called Parton model, namely that the proton is made up of constituents called partons. Part of this Parton model is the fact that the partons cannot exchange large transverse momentum. Transverse momentum means Q, so really large invariant Q squared. That cannot exchange large transverse momentum through this strong interactions, gauge interactions, or gluon exchange. And this statement for the Parton model is valid only at the leading order in the coupling alpha S. We'll see next lecture that that is not true at the next level, the second order. So as I said, classically, or at very high energy, in the quark model we have UU up down quarks, but quantum mechanically, that is at low energy, strong coupling, we have a combination of various quarks and gluons. So it's important to realize that Parton does not mean the up down quarks. It means various combinations of quarks and gluons, real and virtual. But of course, they have to have the overall quantum numbers of up down quarks. So total number meaning the same electric charge, the same isospin, and the same baryon number, and so on. So we consider this this reaction with the incoming electron with momentum k and incoming proton with momentum capital P. Then the quark that's extracted has little momentum little p. Then electron that goes out has momentum k prime, and the photon exchange is with momentum little q, as we said. The quark in here at the end has momentum p plus q. All right. Yeah, so I said that at low energy we have partons that are non-perturbative states, but of course, if we do this at sufficiently high energy, then what we extract is actually a quark. So at least at low, so we said that we exchange momentum that is transfer momentum that is small. I mean, it's not cannot be very large up to first order. All right. So if we work in the center of mass frame and total energy square root s, that is therefore much greater than the proton mass. So that's the meaning of, you know, having a perturbative or deep inelastic scattering. That the overall energy of the collision square root s is much higher than the mass of the constituents, in particular the mass of the proton. So the proton is ultra-relativistic, so it's almost like. And then we will assume that the Parton constituents of the proton have a finite fraction of the proton momentum itself. So they are also almost like themselves, and that also means almost collinear with the proton. Because if the large momentum transfer can only come from gluon exchange suppressed by powers of the strong coupling, then at leading order we can ignore that, and then that means that the partons themselves are almost collinear. So let's consider that the momentum of the constituent parton, little p, is a finite fraction, as we said, a finite fraction that we'll call psi, of the total momentum of the quark that we called capital P. So then the total cross section for the total process is understood as a sum or an integral over the probability to have this finite fraction psi times the cross section where the parton has fraction psi. But of course, the probability to have the cross section the fraction psi is infinitesimal. That is a distribution function, parton distribution function f of psi times d psi. As I said, the partons or constituents of the proton are understood to be quarks, antiquarks, and gluons, either real or virtual. Doesn't matter. So you can, you know, quark and antiquark means all the quarks and antiquarks. So even if if the proton itself is UUD, that doesn't mean that I cannot have other kinds of quarks inside, virtual quarks. So psi is a finite fraction of the momentum. That means psi is in 0, 1, but it's not very small. Not very close to 0, not very close to 1. All right. Yeah, so this is what we said before, the cross section. Then we have, so we have the integral of xi from 0 to 1, and then sum over the various partons indexed by f, with a parton distribution function f of psi, where the index f is the parton. And then I extract the parton qf with momentum psi, capital P, out of it. So the parameters of the the parameters of the interactions, one of the parameters is this momentum squared of the transfer momentum squared. So I'll call, but little q squared is usually negative. So yeah, it's not usually, but it's not negative, it's momentum. So I'll define as minus little q squared, I'll define as capital Q squared. But then, so you extract this parton, but then the basic interaction here is a simple classical electromagnetic interaction, for which we've already done in QFT, in part 1, QFT1, the calculation. And for this process, I'll use hats. So for this process, I'll have, so if this momentum transfer is q, little q, then momentum invariant, the invariant momentum transfer is called, in Mandelstam notation, is called T, but we'll use hats for this basic interaction. So T hat is minus capital Q squared. And then similarly, S hat is P plus K squared, which is 2 P dot K, since P squared and K squared are 0, the objects being ultra-relativistic. And then little p is psi capital P, and then 2 capital P dot K is S, because this is equal to P plus capital P plus K squared, again because the two objects are ultra-relativistic, so they square to 0. So so S hat then is psi S. All right, so we've defined T hat and S hat, and then U hat is defined through the sum of, it's always defined through the fact that S plus T plus U is the sum of m squared of the objects involved in the scattering. But since these are ultra-relativistic objects, this right-hand side is almost 0. So S hat plus T hat plus U hat is 0. That is, U hat is minus S hat minus T hat. Then since also the same thing happens, so in P plus Q squared, well, Q refers to the momentum transfer, which is not large, as we said, but little p refers to the parton, which is ultra-relativistic, so P squared is 0. So then, and then P plus Q itself is also ultra-relativistic, so squares to 0. That results in the fact that we have 2 P dot Q plus Q squared. And again, as usual, little p is psi capital P. So this combination is 0, and then that means that psi, the fraction, equals, so psi was defined as a fraction, so little p divided by capital P, but now is, we've derived that is equal to x, which is by definition capital Q squared divided by 2 capital P dot Q. So as I said, that we have this basic scattering process of electron of a quark, and the formula for that was derived in QFT1 in the last semester. So I'll not repeat it here, I'll just quote it here. We have the reference here if you want in QFT1. So that was the spin averaged amplitude squared was equal to this. And then QF here refers to the electric charge of the parton or quark F that's involved in the scattering, so this one. And then the other object is the electron, which has charge E. So substituting this, then we find that the relativistically invariant differential cross-section for the basic process, that's d sigma dt hat. That is, remember, we have a real differential cross-section, and then we have this theoretical object, the relativistically invariant differential cross-section, that is equal to the real cross-section, both in central maths frame and in lab frame, but not in any other frame. So that was equal to d. So this differential cross-section was equal to d sigma dt, dt hat in this case, referring to the basic process. And that was also defined at this spin average amplitude squared divided by 16 pi s squared, s hat squared here now. And substituting this, we obtain this formula. So then for the total process, I just replace in here t hat by what we calculate to be, minus capital Q squared, and s hat we've calculated to be psi dot s. So we substitute these things, and also substitute the fact that for the total process we have the integral of psi and sum over various partons with the Parton distribution function of this basic and then the cross-section for the basic process. So doing that, we find finally this formula. So t hat was minus q squared. So we find that d sigma dq squared is equal to this thing. Now, substituting, we just get this part. I've introduced also the Heaviside function, theta of psi s minus q squared. That is just to say that the momentum of the s hat is, so for the basic process, s hat is greater or equal than the absolute value of t hat, and s hat is psi s, and t hat is minus q squared. So substituting this, we have that psi s minus q squared is greater or equal to 0, hence the theta of that. So normally then, this would have been a constraint on, so if we had just the basic process scattering of some parton, then this would be just a constraint on the external momenta, so there would be no point in putting a Heaviside function. But now this is not an independent process, but rather part of the full process, right? Because we have a parton with fraction xi, so which comes from somewhere, and then we integrate over this xi. So because we integrate over this xi, then we have to put the Heaviside function. Otherwise, this doesn't make sense. Now, we could also take the second derivative of sigma with respect to x. Remember, x was defined as this thing. But then we have to remember that at the end of the day, we've derived that x is equal to xi. So this sigma dx dq squared basically means that I just remove this integral over xi, right? Because in the end, so I have to derive with respect to x, and then remember that x is equal to xi. So that amounts to just removing xi. So we find this differential formula. And moreover, one usually separates this combination that depends on the partons, this sum over the parton distribution function times the quark, the parton charge squared. Yeah, and also the total charge. Sorry, also the total the momentum transfer to the fourth, capital Q fourth. And one usually writes it like this. The point is that this contains all the dependence on the momentum transfer Q. So it's the second derivative with respect to this momentum transfer squared, Q squared, and x, which is x itself also includes Q squared. And then Q fourth, and then I have also Q squared here. So this contains all the the dependence on momentum transfer, but there's no momentum transfer here. It's only a function of partons, but not on momentum transfer. Well, sorry, yeah, it also depends on x itself. So yeah, it depends independently on Q squared. So it depends on, so you can think of variables as being x and Q squared, right? That's why we derived here independently on with respect to x and Q squared. But so directly on Q squared, we have only on the left-hand side, but on the right-hand side, we have dependence on x here, right? But no dependence on Q. And this relation, the fact that we have this combination of things of the derivative with respect to Q squared and this dependence on momentum transfer on the left-hand side, and on the right-hand side only depends on x, is called Bjorken scaling. So you think of the cross-section as something that depends on the two parameters x and Q squared, and then you have this Bjorken scaling. What this means qualitatively is that so what we're doing is we're probing we collide the electron with a proton, and in this process there is a corresponding momentum transfer that's parameterized by q squared. So we're probing basically with this q squared. So what this qualitatively says that the structure of the process looks the same to an electromagnetic probe. Electromagnetic probe meaning the electron probing via a photon, no matter how hard the proton is struck. So independently on q squared, right? And so this Bjorken scaling is verified experimentally very well, but this is a relation that is true only to first order in the strong coupling alpha S. To second order, we will see there's a correction to that. We'll describe that in the next lecture when we talk about Altarelli-Parisi equation. Another useful variable that one can define is something called y, which is 2 capital P dot q, 2 capital P dot over 2 pi capital P dot k. And here, this in 2 pi capital P dot k, remember, both k, the momentum of the electron, and capital P, that is the momentum of the proton, are light-like, so p squared and q squared is 0, so this thing is S. So this y is 2 capital P dot k divided by S. Now we can calculate this y with respect to the Mandelstam variables of the basic scattering of electron with Parton. So S hat is little p plus k squared, since those are the incoming momenta of the basic scattering, and P and Q, both the quark, the Parton, I should say, and the electron are light-like, so they square to 0. So this is 2 p dot k, and U hat is p minus k prime, and again the outgoing electron with momentum k prime is also light-like, so square to 0. So this is equal to minus 2p dot k prime. So so then, if we look in here, S is psi S hat, but S hat is 2p dot k. So that's what we have in the denominator. In the numerator, capital P is psi dot little p. So we have psi times 2 little p q, which is S hat. Sorry, no, P, excuse me, we have to, in the numerator we have 2, capital P is psi dot P, and Q is k minus k prime. So that's what we have here, 2 psi P k minus k prime. And then we notice 2 pk is S hat, and 2 p minus 2p k prime is u hat. So this is u s hat plus u hat over s hat. But since s hat is greater or equal than absolute value of u hat, we also obtain that so absolute value of u hat over s hat would be, so u hat over s hat from this relation is minus 1 minus y, but then u hat absolute value of u hat be less equal than s hat means that absolute value of 1 minus y is less than equal than 1, which means that y is less than equal 1. And then from the relations we find for y and x, it follows that the products x, y, s is this capital Q squared, this other variable. So then in turn, that means that d psi dq squared, and psi being equal to x, is dx dq squared. But then I write this as dividing by dy, and then divide dq squared by dy is xs from this. So this is xs dx dy. So substituting that, I had the d2 sigma dx dq squared, but now I can replace dx dq squared with d psi dq squared, which is psi s dx dy. So I obtain this relation. So then another way of parameterizing this deep inelastic scattering is that the second derivative of x with respect to x and y times capital Q to the fourth factorizes in two parts, one that depends only on x, here and here, and one that depends only on y. This is the part that only depends on x is the Bjorken scaling factor, and then there's this part that depends only on y, which is, and this division into x and y is called the Cullen-Gross relation. So that's another way of describing deep inelastic scattering. So you note that because of this relation, we don't have three variables. We have just two, but I can describe it in two ways, since these three variables x, y, and q squared are related by this equation. Okay. So what about the final state? I say the final state I called some hadronic state X, but what is that? Well, so what we have at the end of the process in the diagram that I wrote here was well, the original electron, but here I had a quark, and the remaining, well, I didn't describe, I didn't draw this well in the picture in the book. I wrote it 4 lines, internal line, 4 lines here, and then 1 goes here, 3 comes here. So the point is that I take out a parton from the proton, and then I'm left with a remnant and then a quark. And then, but these things are light-like, as I said. They have ultra-relativistic. So they but these things have charge, have gluon charge, which means they cannot live by themselves in the vacuum. They have to go to a state that does not have charge, that is in the that is gauge invariant. So so these things will create these things. The final states will create quark antiquark pairs from the vacuum, and gluon for vacuums, and so on. And experimentally, what you see is what is called a jet. So you have this incoming charged particle, and then it interacts with the vacuum, and it generates other sets of particles. Right? So these things will create the vacuum states must be hadrons. These were by definition the vacuum states of QCD. So what we have is a process that is called Hadron Ization, a non-perturbative process where this initial jet, which is quark or a proton with a parton or a proton without the parton, interacts with the vacuum and becomes a sum of states that are chargeless, that are gauge invariant. Now, this process of hadronization is non-perturbative. It's not something we can calculate through Feynman diagrams. You could perhaps calculate it on the lattice, I suppose, but we're not there yet. That's I think to some degree, some part of it is part of lattice simulations, but there is a complex combination of, for this hadronization, people use a complex combination of non-perturbative either both lattice simulation and experiment to create something kind of a black box, where you put in a parton and out comes probabilities to find various hadrons. Okay, so in experiments, when comparing experiments with deep interelastic scattering experiments with theoretical calculations, we have to take care of this hadronization, and we use it in computer code as a kind of a black box, where this black box is tuned to it contains part lattice, part experiment, and is tuned to agree with some base experiments, and then they are used for others. All right, so that was about the basic deep interelastic scattering, which is the one of electrons over a proton or some more generically some other hadron. But we can consider, and that was something about QCD. But so this was QCD probed via the electromagnetic interaction, via a photon. But we can think of also probing the hadron, or particularly the proton, via the weak interaction, which means the exchange of a W, the W plus or minus, is the particle describing the weak interaction at small, well, describing the weak interaction, what we define to be weak interactions at small energies. But then what does W couple to? Well, so to describe, to have in this, to replace in this basic setup, to replace this probe photon gamma with a W, what one does is to use here a neutrino. So for definiteness, let's consider a muon neutrino. So the process then is like this. So I want something with so the point is, if I use electron probe in here, what dominates the interaction is, what dominates the reaction is the electromagnetic interaction. When I exchange a photon, when the incoming electron pops out, pops out, let's say, a photon. So the final state is a state with a photon and being originally electron. But now I want to probe the proton with a W, which means, and the W has charge, plus, means it will change the pairs in QCD where I started. The pairs were corresponding to SU2 or electroweak pairs. So a W will change one member of a pair to the other member. So in here, then, so if I have W, if I would so if I would hit it with an electron, I could not, well, I could not conserve charge in order to emit a W plus. Well, I could emit a W minus, and then I would get a neon, an electron neutrino, But as I said, the electric interaction dominates that. So in order not to dominate that, to be a clean interaction, I have to start with something that doesn't have electromagnetic charge. So that's a neutrino. So I could put here an electron neutrino, and then through the I would emit W plus, and then the electron. But that's not that's not something that is particularly useful. So it's more useful to use the muon neutrino, which is heavier, and then it will emit a W plus, transform, and the muon will transform, muon neutrino transform into the muon. So this also conserves charge, electric charge, since initial electric charge is 0, final electric charge is -1 plus 1, that's 0. But now also the W also has to turn a member of a doublet into another. So if the quarks are also in doublets, so if I have a D here, it will turn into an U quark. That's the only possibility, because the down quark has negative charge, -1/3, and this one has +1 charge, right? So the only possibility to go from one member of a doublet to the other, and the initial state to have a W with a +1 charge, is this, that it interacts with a down quark, which has negative charge, -1/3, and turns it to a +1 +2/3. Okay, so that's the only possibility for the basic interaction. Muon neutrino pops out a W plus, which interacts with a neutron, but more specifically, which interacts with a proton, but more specifically with a down quark. And then the down quark is turned into an up quark, and the muon neutrino is turned into a muon. All right. What else do I have to tell you here? Yeah, of course. If I had antiquarks, then I could W plus could turn into an U bar, an anti-up quark into a D bar, the anti-down quark. That's another possibility for the basic interaction. But we're talking about protons, and proton has only quarks, not antiquarks. And also note then that I changed from wait, I am doing something wrong. Yeah, I think. Well, if I think about total charge conservation, then I have to. So I guess, yeah, I didn't think about what the rest of it is. But if I have a W plus here, then what I'm probing is the structure of the neutron. The structure of the neutron. So this would be DDU going to UUD, or otherwise the structure of the antiproton. So U bar, U bar, D bar, D bar going to D bar, D bar, U bar. Now, now what's the weak interaction? So I said the weak interaction in here, it's understood as this W plus particle. That turns a member of a doublet into another. But the W plus particle has a very high energy, a very high mass. What is the mass? Well, I'm ashamed to not remember exactly, but I think it's of the order of 100 or 200 GeV. So if you're looking at low energies, at energy much smaller than that mass, what you see is basically a 4 Fermi interaction. So basically, there's no propagation for this thing, because for this W, because it has very high. So basically, the propagator in some interaction. So you see the basic interaction has a G coupling here, a G coupling here, and in between there's a propagator, delta mu over Q squared plus NW squared. But Q squared is much lesser than MW squared, so this looks like 1 over MW squared with delta mu, so contraction here. So this basically means that I just contract this propagator to a point. So that that is what is called a 4 Fermi interaction introduced by Fermi. So 4 Fermi is both because there are 4 fermions and because Fermi introduced it. So this is an effective model for the interaction with this charged gluon, charged, not gluon, charged. Yeah, well, let's call it gluon. Charged massive particle. So Fermi introduced it as a vertex with a coupling G Fermi divided by square root 2, coupling together 4 fermions. So 2 psi bar psi lines. So this Fermi introduced this initially before the electroweak, the weak and then electroweak interactions were understood. So before it was understood that it's a particle of very high mass being exchanged. So then from this this fact, I mean, here I have a contraction over mu, which gives also gives also gives also a factor. But if you compare the amplitudes, so this G Fermi over square root 2 is equal to G squared over 8 mw squared. All right, so similar to the deep interacting, inelastic scattering of electron off of proton, we can do the same thing in here. So the only new thing is that now I have this at low energy. I have this Fermi interaction, so I can write G squared F. So instead of writing G squared over 4 pi w squared mw squared, I write G Fermi squared over pi. And then in here, I will obtain this combination of so the we have the probabilities to have partons up and down inside the neutron. So what to obtain is actually this combination, and the left is the proof is left as an exercise. Oh, sorry. Well, no, yeah, sorry. So here I said. Well, okay, so I said W plus in here, but I could put I could consider the interaction such that this W minus is this is not a final state. W plus is not a final state, but it's rather sort of initial state for this vertex. So I have W minus being exchanged in here, and then this will change oppositely, the up into down. And in that case, I can have the interaction of nu with the proton, generating the mu minus with hadrons. Then what we will obtain will be this, and I left it for you as an exercise, basically using the deep interacting scattering formalism for hadrons, and then just modifying this basic interaction into the 4 Fermi interaction. And then similarly, I can act with mu bar p and obtain a mu plus times hadrons, and then obtain similarly this, which is basically just the bar of that you see here. Well, sorry, I think I have some error there. It should be the bar of it. Yeah, so here is U bar, right? So it's XFD plus X FU bar of X, 1 minus Y squared. And then I just basically here I just exchange U with U bar and D with D bar. So instead of XFD of X, I have XFD bar of X, and so on for this one. All right, there's one more thing to be said here. The normalization of the Parton distribution function. As we mentioned, classically, the proton is made up of the UUD quarks. But quantum mechanically, we expect that there are these partons, which are a strongly coupled mix of states with various QQ bar pairs and also gluons inside the proton. However, the proton certainly at high energy, so perturbatively certainly is UUD. So then that means that the proton has to, and the proton conserves these charges. So that means that the total charges of the state have to be the same. So that means that we can, the way we can state this is that we have two more U quarks than U bar quarks, right? Because we have this, if you think about electric charge and isospin, you see that you should have UU plus UU bar pairs, and then one more D than D bar quark. So because you can have D and D bar pairs, so that translates into the condition that if you integrate over X and you have FU and FU bar, FU minus FU bar must be equal to 2. Integrated must be equal to 2, giving us 2 more quarks than antiquarks. And then the same thing, integral over FD minus FD bar have to be 1, because there's 1 more B quark than antiquark. And then we could also have trace parts of other quarks. In particular, the quark with the next highest mass is the S quark, the strange quark. So usually you consider UD, but you could consider also S. The other ones, charmed top the bottom, are usually always negligible. But for S and S bar, we can say the same, that the integral of S, well, integral of dx, I should say, whatever, Fs minus Fs bar must be equal to 0. So that's for the proton, which is UUD. But I could do the same thing for other kind of hadrons. In particular, the neutron, which just exchange U and D. So FU for the neutron is numerically equal to FD for the proton, and XD for the neutron, FD for the neutron is numerically equal to FU for the proton. And for the bars as well, so and for the S's as well, like this. But Also, another example is for the antiproton. I just exchange U with U bar and D with D bar and S with S bar. So F U bar for the antiproton is Fu for the proton, and Fu for the antiproton is Fu bar, and so on. And finally, there's one more condition on the Parton distribution functions, which comes from the fact that the total momentum of the proton is capital P. So integral of x, x is a momentum fraction, x is equal to psi, which is momentum fraction, of all the distribution functions that are relevant. So for the proton, I write U and D, and well, I can write also U bar and D bar. Sorry, U D and U bar and D bar, because of this relation I also considered the pairs. And then I also consider F for the gluons. So the gluons have none of these charges, but gluons in principle are also constituent Parton. So I have to consider this. So the integral of x of all of these must be equal to 1. So total fraction must be equal to 1. But of course, I could have added Fs and Fs bar as well. That was here, but this is very small. And then for the other ones, other quarks, it's even smaller. Now, these Parton distribution functions are determined experimentally, and then they have to obey all of the normalization conditions that I wrote here. So the way this is done then is you do QCD experiments, and some of them you take as base, and from them you extract the Parton distribution functions, and then you consider those fixed. You put them in a table or some database or something, and then you use them for other QCD experiments. So for completeness, we can consider higher scattering process in collisions of hadrons. So I said the simplest thing was electron with a point-like onto a hadron, or I also told you a muon, neutrino onto a hadron. But the next complicated thing is a hadron on hadron. Now, these both have structure, both have constituent partons. So this is more complicated. But it would still be reduced to, I don't know if I wrote a picture here, I didn't. But anyway, the point is it's still clearly that reduced to a basic interaction, which is parton interaction. So the basic process in the leading order, since we have very small, I mean, our assumption is we have small momentum transfer, which is true in at first order. Then the partons will be just the quarks, and specifically this would be quark-antiquark, and then basically the final state for quark-antiquark has to be just a combination of other hadrons. As I said, this is part of what we understand in Hadron Ization. So the way we describe this is as having two, so each hadron has constituent partons. So there are Parton distribution functions for both. So I have integral of an x1, x2, and ff of x1, ff of x2. And then the basic process is qf plus qf bar going into a hadron. So this would be that's how you would use the Parton distribution functions for this process. But this is much more complicated, so I will not describe it further. All right, so this is what I have to what I had to say here. So do you have any questions? Can somebody verify that you can still hear me?
Yes.
All right, so that means that you don't have any questions. So before finishing, just reminding you that since none of you protested, the next class will be moved to Tuesday at 2 p.m. instead of 10 a.m. Because in the morning I have a meeting, a CCPG meeting for Teoria. So so I'll see you then Tuesday at 2 p.m. Okay. All right. Bye.